Welcome to Advanced Group Theory. Today we are going to explore two of the most fundamental and fascinating concepts in abstract algebra, stabilizers and kernels. These ideas might sound highly theoretical at first, but they are actually the mathematical tools we use to understand symmetry in the physical world, from the structure of crystals to the behavior of complex molecules. By the end of this session, you will understand exactly how to measure what changes and, more importantly, what stays exactly the same. To begin, let us build our intuition. Imagine you are holding a physical Rubik's Cube in your hands. A group action is simply the mathematical way of describing how a set of rules, like twisting the faces of the cube, physically changes an object. Now imagine you want to keep one specific corner piece of the cube exactly where it is. You can still twist other layers, but you avoid moving that one specific corner. The collection of all the specific twists that leave that one chosen corner completely untouched is called the stabilizer. It stabilizes or freezes that specific spot. Now that we understand what a stabilizer is conceptually, let us look at its mathematical definition. This formula tells us exactly how to find it. We read this as G sub x is the set of all elements G in the group G such that applying action G to item x gives exactly x back. Conceptually, we are building a collection of actions. If an action leaves our chosen item x completely unchanged, it earns a spot in this collection. If the action moves x, it is left out. As you choose different items in your set, the specific actions that satisfy this equation will change. This brings us to our next major concept. We just saw that a stabilizer focuses on freezing one single item. But what if you want a move that leaves every single piece of the cube exactly where it started? The only way to do that is to do absolutely nothing. The collection of moves that leave the entire object completely unchanged is called the kernel. To explain it twice, a stabilizer is the list of actions that freeze one specific piece of a puzzle, while the kernel is the list of actions that freeze the entire puzzle all at once. Let us translate that universal freezing concept into a formal equation. This formula defines the kernel of the group action. Just like the stabilizer, we are collecting elements G from the main group G. However, the condition here is much stricter, indicated by the upside down A symbol, which means for all. This equation demands that the action G must leave X unchanged for all possible items X that exist in the entire set X. Because this requirement is so incredibly strict, the kernel is usually a very small collection of actions, often containing only the basic do-nothing action. Before we move on to any proofs, let us see this with a concrete physical example. Imagine a square piece of cardboard sitting on a table. We want to study the mathematical group of actions that allow us to pick up the square, move it, and place it back down. First, we define the set of items we are tracking, which will be the four corners of the square, labeled 1 through 4. Next, we define the group of allowed actions. We use the dihedral group of order 8, which consists of 4 rotations and 4 reflections. Let us visualize one of these specific actions. Here you see our square with its 4 numbered corners. The dashed line represents a diagonal axis, connecting corner 1 and corner 3. The curved arrow shows a reflection, meaning we are flipping the square over along this exact diagonal line. Notice what happens to the corners. Corner 2 and corner 4 will swap places in space, but corner 1 and corner 3 stay exactly where they started. This visual helps us identify which actions belong in our stabilizer. Continuing with our square, we can now determine the exact stabilizer for corner number 1. The identity action E does nothing, so it clearly leaves corner 1 alone. The reflection we just visualized S also leaves corner 1 in its exact original physical location. Therefore, these two specific actions form the complete stabilizer subgroup for that corner. Now, what about the kernel? Is there any move that leaves all four corners in their original spots simultaneously? Rotations move all corners and flips move at least two. The only action that leaves every single corner completely untouched is the identity action. Thus, the kernel contains only E. Now that we have successfully found a stabilizer in a real example, let us prove a fundamental theorem. The stabilizer is always a subgroup of the main group. To prove something is a subgroup, it must pass three tests. First, it must contain the identity element. Doing nothing to the item leaves it exactly as it was, so the identity qualifies. Second, we test for closure. We combine two actions, G and H, that we already know belong to the stabilizer. Applying H leaves X unchanged. Then, applying G to that unchanged X leaves it unchanged again. Therefore, the combined action also fixes X. This brings us to the final test for our subgroup proof, the presence of an inverse. We start with the knowledge that the action G leaves the item X completely unchanged. If we apply the reverse action, denoted by G inverse, to both sides of that scenario, the reverse action must also leave X unchanged. Think of it logically. If walking forward one step leaves you on a painted line and walking backward undoes the forward step, then walking backward must also keep you on that same line. Since all three conditions are met, we have successfully proven that the stabilizer is a fully functioning subgroup. Another crucial theorem states that the kernel is not just a regular subgroup, but a normal subgroup. This means it remains unchanged when sandwiched between an outside action and its reverse. To prove this, we take an element K from the kernel, surrounded by G and G inverse, and apply this three-part combination to an arbitrary item X. We evaluate from right to left. The reverse action creates a new item. But remember, K is in the kernel, so it leaves absolutely every item completely unchanged. Therefore, K acts on this new item and simply spits the exact same item right back out. Continuing our proof, we now resolve the final outer layer of our sequential action. We are left with the action G being applied to the result of the reverse action applied to X. By the fundamental definition of how inverses work in group theory, an action and its exact reverse perfectly cancel each other out, leaving you exactly where you started. The result is simply the original item X, completely untouched by the entire three-part sandwiched operation. Because this sandwiched operation leaves X unchanged, it belongs to the kernel, proving that the kernel is indeed a normal subgroup. So, we have proven our core theorems. This brings us to a more abstract scenario that is incredibly important in advanced mathematics: action by conjugation. Instead of a group acting on a physical object, like a square, we will look at a group acting on its own internal elements. This might seem abstract, but it is essentially a mathematical way of changing your perspective or coordinate system, applying an action and then changing the perspective back. It is one of the most important tools for understanding the hidden internal structure of any group. Let us look at the mathematical rule for this internal action. This formula defines conjugation. The action consists of taking an element X, multiplying it on the left by an action G, and then multiplying it on the right by the reverse of G, which is G inverse. This three-part multiplication is the formal way we change the coordinate system, perform the operation, and return to the original coordinates. If the variable G changes, the perspective shifts differently, altering how the internal elements interact with one another. Now that we have our conjugation formula, let us find the stabilizer for a specific element X under this action. We start by setting the result of the conjugation action exactly equal to the original element X. In plain English, we are looking for all the specific actions G that when used to sandwich X end up not changing X at all. Any action G that makes this equation true will earn a spot in the stabilizer for X. Our next step is to simplify this equation. Continuing from our setup, we simplify the equation by multiplying both sides by G on the right. The G inverse and G on the left side cancel out, leaving us with a beautifully simple relationship. G times X equals X times G. This equation says that doing action G followed by action X gives the exact same result as doing action X followed by action G. When two actions can swap their order like this, we say they commute. Therefore, the stabilizer of X is simply the collection of all elements that commute with X, which is famously known as the centralizer. To summarize our journey today, group actions describe how mathematical rules physically affect a set of items. The stabilizer is the specific collection of actions that freeze one particular item in place, acting as a localized do-nothing command. The kernel is the universal collection of actions that freeze every single item in the entire set simultaneously. By studying what remains unchanged during an action, we unlock deep insights into the hidden symmetries and structures of both abstract mathematics and the physical world. You have now mastered the foundations of stabilizers and kernels.